Okay, so as I said, now we have the second set of lectures of Héctor Sánchez, so please go ahead.
Great, thank you very much. Well, also, happy to see everyone again today. So yesterday we discussed and talked a lot about how to create general relativistic magnetohydrodynamic or GRMHD models of hot accretion flows. So if you remember, there was a pipeline that was used to create synthetic observations. So we started from a space-time model, then using that space-time model as a background, we performed GRMHD simulations to simulate the behavior of plasma on top of that space-time. Then we performed radiative transfer calculations in order to simulate the behavior of light that is emitted from that plasma and traveling through the space-time. And finally, we applied the uncertainties associated to the instruments and the observing conditions. So today we will focus on the middle step of this process, that is how to perform radiative transfer calculations, or actually, how they are performed. So since in the previous talk and also in the talk in Monday by Gonzalo Olmos, there was already a very detailed revision on how ray tracing works. We will focus more on giving a general picture of it. And this will be for today. I will try to be more brief in this theoretical revision and to give a bit more time for the practical part of the session. And finally, tomorrow we will see this applied to the goal of imaging exotic compact objects. So, the radiative transfer step consists on simulating the behavior of matter from when it is emitted to the plasma, when it travels through plasma, and when it follows the curved paths of space-time. So it consists of two parts, as we saw just in the previous lecture. So on one hand, we have to solve the geodesic equation to find what are the paths that light will follow. And on the other hand, we have to solve the radiative transfer equation to see how the intensity and polarization of light changes as it travels through the plasma. So, for solving the geodesic equation, many times we work backwards. So first we find what is the trajectory that the photon will follow. And once we know that trajectory, we integrate forward from the source to the observer. This is the radiative transfer equation. As you can see, it is a matrix equation. So we solve for the total intensity of light and for the three Stokes parameters that give information about the polarization. The content of this of the right-hand side of this equation has first the emissivities. So this will tell us how much radiation is emitted at a given location of the plasma. And then it has this matrix that contains the absorptivities that are these alphas that tell us how much radiation is absorbed by the plasma along its way. And we have these rows that are the so-called rotation coefficients that tell us how much radiation is converted from one type of polarization into another. So, then in order to find what are these coefficients, we need to know the radiative processes that are taking place in the plasma. These are mainly the process that I have listed here. So we have synchrotron radiation that is associated to having a very ionized plasma and a magnetic field. We also have Bremsstrahlung that is associated to having very, very hot plasma, and you know the mechanism is radiation from accelerating charges. We have also Compton radiation that is scattering, and for very energetic photons, so for the range of gamma rays, we may see effects from pair production. However, at the wavelengths that the EHT is typically observing, we have mainly only synchrotron radiation. So this is a spectrum that was constructed from a simulation using another type of code that is not a typical ray tracing code, but is called a Monte Carlo code. So here you can see that there are different bumps that correspond to different types of radiative processes. We have first this larger bump that is precisely what it becomes most important at the observing frequency of the EHT, that is 230 gigahertz. And then we have two bumps at higher frequencies that are associated to the same synchrotron radiation being scattered once and twice in the process that is called inverse Compton, that energizes more the radiation after each scattering. So as you can see, it starts in radio wavelengths, but then after the radiation is scattered, it goes to even to infrared and X-rays. So this type of codes, Monte Carlo codes, are also codes that perform ray tracing, but they work in a very different way. So as we were seeing in the previous talk by Gonzalo, typically, ray tracing codes work by selecting a screen and then integrating backwards the geodesics up to the source. This is very efficient if we want to form an image, because in that way we don't have to waste our time and resources in integrating geodesics that are not going to reach the observer. However, in the presence of scattering, this adds a degree of unpredictability on where radiation is going to end. Because well, radiation hits an atom, and then it will change its trajectory with some probability depending on how it hits the atom. So that's why for Monte Carlo codes it is not possible to do backwards ray tracing. So one has to integrate from the source, then well, simulate the scattering process using precisely the Monte Carlo method. And then one places a lot of detectors around the domain of the simulation. That can be something like a sphere. So, well, this is how it works, and we need Monte Carlo methods in order to calculate the full spectrum of, for example, Sagittarius star and M87. However, for images at the observing frequency of the EHT, we only need a traditional or simpler radiative, so a typical ray tracing code. So, well, for integrating numerically the geodesics, there are several methods. So there is something that is very popular and also very simple is the Runge-Kutta method of fourth order. However, there are also other methods that are a bit more sophisticated. For example, there is the Ferlet method that has this property that is also used for for integrating trajectories, for example, in mechanics. So that it has this property that preserves the volume in phase space, so that it can better preserve some of the constants of the motion. This is important for other types of dynamics. So, for example, so this property of preserving some invariance of the motion is very important when doing particle in cell simulations. But for radiation, well, there are a lot of codes that use plainly the Runge-Kutta method and work very well. And finally, something that is also very popular is to use adaptive steps. So this can be used both at the time of integrating the geodesic equation, but also at the time of integrating backwards the radiative transfer equation. So one can decrease the step size depending on whether the equations become more challenging to solve. This could be, for instance, because of having big gradients in the metric, or also because having very abrupt changes in the opacity of the plasma. So, as I mentioned, one of or actually the most important radiation process that occurs at the observing frequency of the HT is synchrotron radiation. So this synchrotron radiation is also associated to charge being accelerated. So it is also associated to momentum being drawn away from charges and going into the electromagnetic field. And then for this reason, it is also known as Magneto-Bremsstrahlung. So how it works, it is like this. So one has, in this case, a magnetic field line that is propagating outside of the page. The charged particles are rotating around the direction of these magnetic field lines. And because they are, they have some centripetal acceleration, they are changing their momentum, and they are getting rid of some of their linear momentum via radiation. So, we have seen that there are some ingredients that participate in this process. So one is the magnetic field. Another ingredient is the velocity of charges that is related to the temperature of charges. And another ingredient will be how dense the plasma is, because the more particles, the more intense synchrotron radiation we will get. So, although in general this radiation is hard to calculate, so the emissivities and especially emissivities are hard to calculate because they involve some wild integrals. It is possible to have some approximations that work for the frequency at which the EHT observes, so that this is for a transparent plasma of emitting at 230 gigahertz. So, and this is precisely one of these approximating formulas. So, as you can see here, we have some of the ingredients that I mentioned. So we have the number density of electrons, and we have this exponential that contains, other quantities. But in the quantities that are in this exponential, you can see the electron dimensionless temperature and the magnetic field. So you can see that this is a negative exponential. So the higher the temperature, this will mean more synchrotron radiation, so more intensity in the radiation, and also the higher the magnetic field, will also increase the intensity of radiation. So this is precisely as we expected, no? So it has all the ingredients that we could intuitively imagine from this picture. So the more magnetic field, the more particle number density, and the more temperature, in general enhances the synchrotron emissivity. But now, as you have seen, we did this for the case of synchrotron radiation emitted from the electrons. Now, there is one important thing that is necessary to take into account when going from GRMSD simulations into radiative transfer calculations. And this is that electrons and ions will have in general different thermodynamic properties. This is because they will cool by different mechanisms. So, for example, the electrons are more susceptible to be accelerated by magnetic reconnection. On the other hand, ions will be more affected by the dynamics of the plasma, and therefore will be more sensitive to, for example, dissipative effects at the bottom of the turbulent cascade. So in general, they will have different thermodynamics. And this is a bit problematic because for GRMSD simulations, what we simulate is mostly the behavior of ions that are the part that have more inertia, and is the part that is mostly affected by the dynamics of GRMSD. So, this means that we will in general have large uncertainties in electron temperature. And it also means that we need a way from going from the temperature that we get from GRMSD simulations to the temperature that the electrons will have, and that will determine the observable properties. So currently, what is the standard to use in order to go from simulations to radiative transfer calculations is the parameterization, what is called the R-high, R-low parameterization. This was from a paper by Monika Moshibrodska from 2016, and it works in this way. So we have a quantity R that defines the ratio between the ion temperature and the electron temperature. And then we defined a value for this ratio for regions of high magnetization and a value for this ratio of for regions of low magnetization. And then simply this formula interpolates between all the regions so this formula interpolates between regions that have the value defined for high magnetization and the value defined for low magnetization. So these parameters, R high and R low, are free parameters that need to be constrained by observations in general. It can be that for example, according to some model, the value R high will be larger than the value of R low, or it can be that it is completely the other way around. But this is something that needs to be tested. Sorry. So B is the magnetic field intensity in the fluid frame. Right. So, well, as you can see, then this fraction tends to 1 if the magnetic field intensity is large, because this will tend to B squared over B squared, and this other side will tend to 1 if the magnetic field intensity is very small, no? Because it will become 1 over 1. So, so typically one uses this formula to interpolate. However, well, the actual situation may be quite more complicated. So this assumes that that both electrons and protons will have a well-defined temperature, and this means having a distribution function that is similar to the Maxwell-Boltzmann or Maxwell-Juttner distributions. However, in the presence of effects such as magnetic reconnection, electrons are expected to also be accelerated, and this will take some of the electrons out of the Maxwell-Boltzmann or Maxwell-Juttner distribution and put them into what are called non-thermal tails. So, something else that people have tried to do in modeling spectra of black hole accretion disk is to include these non-thermal tails in the electron distribution function, and this is for example what is called the kappa distribution. Something else that people have been trying to do quite recently is to try to go beyond this prescription that has these two free parameters and compute from first principles what the appropriate ratio between electron and proton temperatures would be. However, in order to do that, one has to go beyond the fluid approximation and use other techniques that are called particle-in-cell simulations. So these are kinetic simulations. So people take a small patch of the accretion disk and simulate directly the motion of ions and electrons subject to a magnetic field. And after some time, they calculate what is the ratio between the electron and ion temperature, or also optionally what are what is the actual distribution of electrons. So, this is actually this work that appeared recently is quite interesting because it reveals that even though this formula is reasonably correct, the ratios seem to be more sensitive, not directly to the ratio between magnetic pressure and plasma pressure, but more to the ratio between magnetic pressure and plasma density. So, this is still something that is an active area of research, but it is possible that the community is moving towards calculating these ratios from first principles instead of fitting them to simulations. Right, but so this is about the temperature of the plasma and the temperature of electrons and how you can get emissivity from there. But there is also something that is very interesting about synchrotron radiation, and this is the fact that synchrotron radiation is polarized, and because it is polarized, it carries additional information in the polarization. So, well, previously we saw that synchrotron radiation comes from charges that are accelerating with centripetal acceleration around magnetic field lines. So, because this motion is confined, so the acceleration always happens in a direction normal to the magnetic field lines. This will also give a preferential polarization for the radiation that the electrons emit. So in general, we can expect that if we project on the sky the polarization angle, the polarization vector of radiation, this will be orthogonal to the projected direction of the magnetic field. This is not so trivial, and especially if one has a curved spacetime. This will be, and also where the light rays don't follow straight geodesics, this will be a bit less direct to interpret, but in general, one can think that roughly the projected magnetic field will be orthogonal to the polarization direction. So, for example, in this image of Sagittarius A star, we can see this line that has been drawn that corresponds to the polarization field. So there is a common misinterpretation about this image, assuming that what we see is the magnetic field, but actually it is the other way around. So what we are seeing is the polarization field, and roughly the magnetic field should be orthogonal to these lines in the approximation of no curved spacetime. However, still there is something interesting that we can learn from this image, and this is the fact that the polarization seems very, very coherent. So the fact that we have a polarization that is very coherent and not scrambled means, in general, that the magnetic field has to be coherent as well. And if you remember what we talked about yesterday about these differences between the sane accretion regime and the mad accretion regime, probably you remember that in the sane regime is characterized by small-scale turbulence and also small-scale changes in the magnetic field, while the sane regime corresponds more to large-scale magnetic fields and large-scale magnetic stresses that drive accretion. So, having a well-ordered magnetic field is another observable that favors the math model.
We can ask questions. So you're saying that we should think about magnetic field as being orthogonal more roughly to those. We have a plane orthogonal with this direction and the one projected on the plane. So do we have any information about, if it's the magnetic field as a component also orthogonal to the plane? Is what I'm saying? Yeah, there's a plane orthogonality with respect to those lines. So what we know.
So, that is actually a good point, because this is something that always happens in astrophysics. So we have many times we cannot look exactly at the three-dimensional structure of something. So it is like what we were talking about yesterday about the mass accretion rate. So many times we only have access to quantities that are line integrated, no? that are line projections. In this case, it is quite similar. So indeed, there is some part of information that we are missing because we have a particular observing plane. So. Sorry.
The longitudinal component Carlos is talking about, there wouldn't not be a wave solution, right? There would be I don't know, a dynamic field, but not
Right,
a
that's true. So exactly so we know that there cannot be a longitudinal wave, no, because then this will violate the Maxwell constraints.
Exactly.
But still,
Talk about magnetic field itself. Just a minute. Just
right.
So because you could think, I mean, if the spin axis would be like this, which we don't know where it is, and you have, kind of matter orbiting around, you'd expect exactly to have component of the magnetic field.
Exactly, and so in addition to this, there is also something that we don't know, which is how much the orientation of the polarization vector changes in its way from when it is emitted to the location where we observe it. And so, for example, well, something that I wanted to also mention in this slide is that for the observations of Sagittarius A star in polarized radiation that were published in 2014. There are some things that don't totally make sense if one compares the models that are favored in the by polarization constraints and those that are favored by total intensity constraints. So, for example, if one doesn't, so if one just plainly compares the models that are favored by the two constraints separately, it seems that so that a particular set of models is favored by the total intensity constraints, and this model seems to be no longer favored by the polarization constraints. So this small single green region that I showed you yesterday in the pizza plot is not one of the models that is favored when applying plainly the polarization constraints. However, then if one considers that there may be a screen between us and Sagittarius A star that applies Faraday rotation to the radiation that is incoming, then one can well recover that the same models that are favored by polarization are also favored by the total intensity constraints. So. So yes, this is sensitive to the three-dimensional structure, and also there is some modeling needed in order to be able to know what is the effect of this screen that may be there, and that actually it makes a lot of sense that it's there because we are looking at the galactic center. So there may be well a lot of plasma that is also magnetized and well going. Polarized radiation going through a medium that has that also has a magnetic field produces precisely the Faraday rotation.
So I seem to remember, I'm not sure if it was for Sagittarius A star or M87 star, but that when these measurements came out, that they favor the poloidal magnetic field rather than a toroidal one.
Right.
Am I remembering correctly?
No, so I am a bit confused now.
Yeah. Well, I have this recollection that they mentioned that from the information from the polarization in M87 star, a poloidal magnetic field was preferred. And so maybe I'm confused, and you seem to be confused, so that may be confirming that I might be confused. But anyway, so if you don't recall, then we can discuss afterwards.
Well, I think that what should be preferred is a toroidal magnetic. Probably I know what you are referring to. So there were 3 observations at different epochs of M87.
Yes. So
well, the first observations are. Fit very well with what was was predicted. No, so they show a toroidal magnetic field that is and also some magnetic field that is very coherent, and it's also a magnetic field that has the signatures of energy extraction. No? But then the following observation shows something that is much less coherent. and that favors the opposite orientation of the magnetic field. And then, well, the observations that were performed in the third epoch also show something that is a bit, so that seems again a bit more coherent, but it's in the wrong side. That doesn't show energy extraction, but it shows energy absorption by the black hole. No? Probably that is what you are. So, well,
I'll look it up, and then I'll.
But well, if that's the case, actually, this is one of the things that are not completely resolved by theory. No, so this is one of the things, one of the places where theoretical modeling needs to do a bit more effort to account better for the observations. So, right. So, well, we have seen so far what are the radiation processes that are used to simulate the appearance of the black hole from the time where radiation is emitted and while it propagates through the plasma. But there is one additional layer that is how this radiation is finally received by telescopes on Earth, and how well it is, so how it is sampled, and how this is then used to build an image. So I will then go very briefly over it. So what we look when observing a source using a very long baseline interferometry is not directly an image. So what we measure on Earth are correlations between when a signal is received in one telescope and when a similar signal is observed in another telescope that is separated by some distance that is called baseline. So this is something that can be, that is a setup with some similarities to what happens when one has the double slit experiment. So radiation that has some coherence will hit two detectors that one can think of as the holes in the double slit experiment and produce an interference pattern. So this interference pattern will be related to the Fourier transform of the actual source on the sky, and then it will, and then what this results is in that we don't have precisely an image of the source that is being observed, but we have a collection of points of observations that are sampled in the Fourier transform of that image. So a specific pair of telescopes is associated to a baseline, and then a baseline is associated to 2 points that are associated to 2 points in the Fourier space. So 2 points that are symmetric. So one is associated to the forward distance from one telescope to the other, and the other one is associated to the backward distance between the same pair of telescopes. And then, well, at each of these points, we sampled 2 quantities that describe each of the complex numbers. One of them is the amplitudes, and the other one is the phases. So even without trying to convert this into an image, as those that well are normally seen as the main result of DHT. So even before doing that, one can already get a lot of valuable information from looking at the amplitudes, for example, or at the phases. So, for instance, this plot shows just the amplitudes for the absolute value of the baseline. So one can think of it as these observations in the Fourier plane condensed over a line. So we are plotting this just over the radius in the Fourier plane, and one can see that there are 2 places where the amplitudes become very close to 0. So these places are called nulls, and so by well, performing a Fourier transform, one can see that the first that if the original image is a ring, the first null will be associated to the diameter of the ring and the location so it will be associated only to the diameter of the ring. And the second null will be associated mainly to the thickness of the ring. So in principle, one can perform constraints on what is the size of the ring even before calculating an image. But of course, the information is much easier to interpret if we try to transform this into an image. And then the main problem becomes how to fill the parts of the UV plane or this Fourier plane that are not sampled. So this is just an example of how how the Fourier transform of an image looks like. But you already know. So the Fourier transform is sensitive to frequencies, and therefore, so in this image of a windmill that has some periodic structures like the fact that we have 4 blades of the windmill, and the fact that we have this periodicity in the structure of each blade translates to points that are particularly bright on the Fourier plane. So, however, here we only have a few samples, and we need to interpret or to fill in all the remaining parts of the Fourier plane. So how to do it is a big problem, no? So in some sense, we have to invent some of the information or to make an educated guess on what we may have there. Fortunately, our expectations is that the image of Sagittarius A star or MET7 will not be as complex as the image of this windmill, or it will have some a bit more smooth structure. So there are different methods that are used to recover the missing information. One of the methods that has more tradition that has been used for a long time is called the clean algorithm. And this method tries to fit Gaussians to the points that are observed. So it employs a certain number of Gaussians, because they have very nice properties when going back and forth from the image plane to the Fourier plane. And then, after getting some good number for the chi-square, it is able to reconstruct an image. In the HT, there were several reconstruction methods that were used. This clean algorithm that I mentioned was used for the reconstruction algorithm that is called diffmap. But there were also other methods that were used. So here I am putting also some images that were reconstructed using a software that is called EHT imaging and a software that is called Smiley that use a different method that is called regularized maximum likelihood, and that essentially tries to define some loss function or some functions that needs to be optimized, and tries to also fill the UV plane in such a way that one minimizes that function subject to some constraints. So, as I mentioned, I didn't want to take a lot of time to this in this part. I would like to go a bit more towards the practical side. So, to give a summary of this second session, this will be the main takeaway points. So, something important to remember is that at the observing frequency of the EHT, synchrotron radiation is the main emission mechanism. Also, this emission depends on the local thermodynamic properties as the electron temperature, the electron number density, and the magnetic field. Also, electron thermodynamics is important, but there are large uncertainties because it is not completely well known how to go from the GRMSD simulation that has the ion that gives the ion temperature towards the electron temperature. But currently, the plasma beta prescription is the standard, and there is work on improving on that prescription. We also saw that synchrotron radiation is polarized. This polarization contains information on the structure of the magnetic field, so it's valuable to have it. And we also saw that space-time geometry and the medium between the source and the observer can alter this polarization. And finally, well, in going from this calculated image using radiative transfer codes towards the images that should actually be compared to observational data, or actually to synthetic observations that can be just the baselines and just the amplitudes and phases at a given baseline. Very long baseline interferometry samples the source in the Fourier plane, and from then reconstruction is needed to produce images. So, well, this was the theoretical part. Then, if it is okay, maybe we can have a short 10 minutes break before going to the practice part. And if there are some questions,
I will ask. So, let's. Do we have any question for this first part? If not, let's have a 10-minute break. Okay, so now we have the second part of the morning lecture by Héctor. So please go ahead.
Thank you. Well, thank you very much for following me up to here. So, well, now we will try to learn how to use a code that considers all that, or almost all that we saw during the past hour. So this will not do the part of doing the image reconstruction and that, but it will take us from the geometry simulation to obtaining an image that was ray trace and solving the radiative transfer equation for the case of synchrotron emission. So we will turn a geometry simulation into something that looks like that. So this code uses polarized radiative transfer. So in addition to the imaging total intensity, we will also get the four source parameters. So the code that we will use is public, similar to the code back that we use in the for yesterday's session. And actually, well, it was designed a bit to be the partner of back. So it accepts the format of back, and it is also built with a similar architecture that one keeps the main source code in one directory, and one can well, keep it modular and use a different folder to set up the simulation. So in order to get to this code, if you want, you can follow me. By the way, yesterday there were some things that were not covered, so like visualizing the simulation or performing a thorough simulation. But I will try to cover them after I finish this part. So then feel free to follow on your laptops. So the first thing that we will do will be to check out the Git repository of the code. So you can go to this website. So gitcode.com/Jordi Avelar. Jordi Avelar is one of the main developers of this code, and then go to Raptor, which is the name of this code. So I have already opened it here. And so if you scroll down sufficiently, there is a tutorial on how to build images and vector. For this session, we will try only the tutorial on creating images. So, but first we have to get the code. So similar to yesterday, I will start from getting the code from GitHub. So to do that, we So we have this folder that was called codes. Then I will just go inside of it. We still have a back here, and then I will clone GitHub. I will clone a route from GitHub here. It should be very fast. Well, more or less.
Could you scroll up to the directory again, the URL which should be
Sure. Or well, if you are looking for the URL, maybe it's better that
Oh,
I
yeah,
go
that's
for
fine,
it.
And was there anything else after you cloned this one?
No, so you just go to the directory where you want to clone it and just git clone the
Or what's your username? Okay. Okay, yeah, it's
well, if you just write git clone, you have to add .git at the end of this.
Oh, not Git.
Right. Or if you go to the Git repository,
It still wants a username.
I see. That's very strange. If you
No worries, I always have this problem. That's why I don't use it.
oh, I see.
It's all never gets one.
That's very important. But actually it's the same. So would you use the HTTPS option or?
I just follow what you typed. But it seems you need some registration that I don't have. That's fine, don't worry.
Okay, well, I don't know how it's working for the others. Is it okay? Someone else is trying? Okay, sure. Okay, so well, here it has finished downloading. Well, I am thinking if it fails with cloning from Git, one can always download the zip.
Ah, yeah, on the web page.
Right. So now, similarly to when we installed back yesterday, we need to tell the computer where to find the code. So we can take this part and write it in the bash RC file. So here, similar to back, I already have it in some directory, but I will comment out it and create a new a new line with the same environment variable, but pointing to the directory where I just downloaded. It should be wrapped. Okay, now that I added this line to the bash.rc file, I need to do source again. and now it should be there. If I ask it what is the value of this environment variable, I will return the directory where I just downloaded. Then, so now that the Raptor is downloaded and that we have all the computer where to find it, we can start following the tutorial. Okay, there was something else to do. So this, so Raptor also comes with some dedicated visualization scripts. So it is recommended that you add these these tools to your Python path. In my case, I also, I also already had it here. So I will not do it again, but here, the important thing is that actually it do the check because here this, so this line already takes the paths that we define in Raptor, so to the location of the Raptor directory, and it just goes inside of it with Python, the plotting, and this just turns into append into the Python path. So you can just copy this line exactly as it is and put it below the line that you added in the bankruptcy file. And also, as we mentioned yesterday, if you are working with Mac OS, then instead of RC, it should be the file set shrc. So, now that we have set up this, then we can start with the tutorial. While I explain, I will start downloading some geography data that was already prepared with the code pack that is located somewhere online. And because this data it can take a bit of time to download, I will start the process of downloading while I explain. So this you can find in the step 2 of the tutorial. So you can get this file from this address. Here I will do it in a different terminal. And you can see that it is downloading. So it is this is a roughly 200 megabyte file. So if you have a fast connection, it should not take a lot of time, but it depends. And then, in the meantime, let's start setting up Raptor. So as I mentioned before, this works in a very similar way as back. So we will create a new directory where we will put the simulation and call a configuration script with some parameters that will tell the code which options to choose when compiling. So we go out of the codes directory, and here I will create a new directory that will be called Raptor Run. Then I go inside it, and here I will call the configuration script. So this is also called setup.sh. And I will start giving the options that I need. So these options, let me these options are the following. The first option tells the type of metric. In this case, this is modified Hershey coordinates. So this is a kind of Hershey coordinate with some stretch in the theta direction and with logarithmic radius, which is something good for geometry simulation. So the simulations that we will be reading are in that type of coordinates. The second graph tells what type of data are we going to ray trace. So -C stands for code. So we are going to read data that is in the format of the code back. So, but it has another option to read data from the code part. Then the next parameter tells it that it will perform polarized radiative transfer because it has the option to perform unpolarized and polarized radiative transfer. Unpolarized is faster, but we want to show the full capability, so that's with polarized radiative transfer. And finally, the last parameter is something that is a bit technical, so it's not related to physics, but it's related to how the data is arranged in the geometry simulation. So SFC stands for space filling form, and this is just a way of ordering the blocks in the AMR simulation so that one minimizes communication. So the data that we will read uses this feature of the back code. So just because of this, we will include this flag. So then let's start running the configuration script. Okay, so here there is something wrong. Here there is a problem with my Honda configuration that is missing some. Well, it is missing the compiler, but this is not a problem. So most likely you are working on Linux, you have the right compiler, and then the only thing that we will do will be Honda the architecture. If you are working on, so if you have everything set up well in your Honda environment and you want to use a Honda environment, you don't do this. But so in my case, now I am starting as if it was fresh. So okay, now I will run again the configuration script. And now the compilation was successful. So if I do LX, I will see that there is an executable that was created that is called Raptor. But before running, let's see what happened with the file that we were downloading. So it seems that this file already finished downloading, so it downloaded successfully. And it is this file that is called data2000.dat. So having this, well, we can start running Raptor in order to do the ray tracing. So just to have everything exactly as it is in the tutorial, I will move it inside the directory Raptor runs that we created. So now we also have the geometry data in the folder. So now we will tell Raptor to ray trace this data. So let's just copy from the tutorial. And here what we are doing is to execute the executable. We will take the parameter file model.in and ray trace the data that is in data2000.dat. And then again we are giving we're giving number 0. This is because so this is the file index of the output. So if blocks of some number of pixels by that number of pixels. And because the code is parallelized with OpenMP, if you have several CPUs and if you have and if you tell the OpenMP flags to execute the program with a given number of CPUs, it will split among those and it will perform the radiative transfer calculation in parallel. So now it has finished. We get some additional information and essentially that's it. So after doing this, we can produce an image. This additional information that we get is the frequency as we were observing. So in this case, it is 230 gigahertz, the observing frequency of the EHP. And we also get the integrated clock density that is 3.63 Johnson. So, well, now we can do two things. Maybe let's first look at what is the image that we get, and then we will go explaining what are the parameters that were given in the parameter file. So, as I mentioned, Raptor comes with its own visualization tools. So this is the line that I suggested to add to the Python path in the bash file. And then, but because now this is added, we can simply copy the plotter example from these tools and try to run. So we will copy from the Raptor source directory, Python, plotting, and then plotter example. So we will copy to our directory. Now it is here, and we will simply run. Plotter example.p, and we again give the index of the snapshot that we just ray traced. Apparently, I am missing the modified API. The modified API. Okay, but this is no. So this is not worry. This is something that you have to install in my case. So now I'm missing it precisely because I went out of the content environment. But if I get back into the content environment, it will be there. Well, if you don't have it, you have to also install it using Conda or whatever you use to install Python modules. So in my case, I will just do Conda activate again. And if I run it will, well, now it's running. He's complaining about some fonts that are not found, but this is not a problem. Now we have finished running, and it has created a directory that is called figures. So let's have a look at the output of what is there. So I will just open it with my image viewer. You can open it with the image viewer of your choice. And it was in figures, and it is this image 0. So let's have a look. And when this looks beautiful, as you can see, we have the image in total intensity. We have the image in the 3 scope parameters. And as you can see, this is already given in the scales of well, in this case it's milliard seconds, but it is already in the physical scale that will correspond to the actual observations of this. So it is given in the actual size that it will look for telescopes on the Earth, let's say. So, well, now that we have shown the look again at the parameter file and see the parameters and how it relates to the explanation that I gave previously about about the radiative transfer. So let's look at the parameter file that was called model.in. So these are all the contents of the parameter file in this case. So first we have the mass of the black hole. This is, as you can see, this corresponds to the mass of Sagittarius A star. This is roughly 4 million solar masses. Then we also need to provide a distance. Also the distance Sagittarius A star. And so these two numbers, the only thing that they are used to is in order to give the appropriate size of the image in the sky. So the mass of the black hole set as a scale in length units. That is the scale of the gravitational radius, and the distance sets an angular scale, because then that scale in gravitational radius, if we divide it by the distance, we get an angle. So that angle is will be the size of the scale in so it could be the scale of the image on the sky in arc seconds after appropriate unit conversions, of course. Then here we have the parameters for the high and low parameterization that I mentioned. So in this case, both of them are 1. So we are setting the temperature of electrons equal to the temperature of ions, regardless of the magnetization. It is just the same temperature everywhere. I mean, the same temperature ratio everywhere. And then, so here finally there is one extra physical parameter that is called the mass unit. The reason for this physical parameter to be there is that only one produces a scale for density, so the DRHT simulations are invariant with respect to rescaling. So this is because the equations of ideal DRHT are rescalable to with respect to the density scale. So the quantities that we get out of these simulations can be expressed all as a ranges. So we have something physical that we can extract from there is, for example, the sound speed that is given in units of the speed of light. And the sound speed so the sound speed squared is proportional to the ratio between pressure and density. And so something else that we get is the advent speed that is proportional to the ratio between the magnetic field in the fluid frame and density. So if we scale the density by a factor, we will get exactly the same simulation that we would obtain if we scale the pressure by the same factor and the magnetic field by the square root of that factor. So this provides a freedom to rescale the density scale in the simulation. However, the radiative transfer calculations are not insensitive to these changes in scale, so they are affected by them. And then, and what the way we will see that it's affected is by looking at the total flux. So when regressing simulations, we will try to match the total flux that is observed in Sagittarius A star or in M87. And then we should adjust this mass unit until we get a total flux that is compatible with observations. So as I showed you when I run the simulation, the total flux is actually one of the output parameters that we get. So one should, when requesting a completely new simulation, one needs to iterate, running several times with different mass units until the total flux is consistent with what we see in observation. And finally, the rest of the parameters are parameters of the image. So we have the observer's inclination. In this case, it is 50 degrees. Then we choose the image size in pixels. In this case, it is 200 by 200. And then we set the size of the camera in gravitational gradient. In this case, it is 40 by 40. And well, this part is if we want to calculate the frequencies, well, the image that have different frequencies, that is something that is useful for calculating the spectrum. So, well, so this is it in general. This is just to give some information on how to get the spectrum, how many frequencies per decade you want, where to start. Then this is something. This is the step size for the numerical method, and this parameter is because this code also uses adaptive refinement to calculate the images, and then here it is just setting the maximum level of adaptive refinement to 1, which means not using adaptive refinement. So we are calculating the image at a uniform resolution. And well, that is essentially how to operate this code. Okay, now so we still have 10 minutes of time, and perhaps maybe I would like to ask you what would you like to do in these next 10 minutes. So something that we could do would be to answer questions. I could also show you how to run a simulation of a torus, of an accreting torus. Or yesterday there was also some interest in adding custom stations to back. So, for example, numerical text. So I don't know if there is any preference of what you like to do.
I think the torus
The torus?
would be nice.
Okay. Good. So, well, for running the torus, actually in the tutorial that or in the set of tutorials for back that I showed you yesterday, in the third session, it explains precisely how to run a torus simulation. So you can go to the website of the code back, go again to documentation, and then check out session 3. Here, well, I will simply follow the steps that are here and explain what are you doing at each step. So, let's go again to our old directory of backgrounds from yesterday. And now we will copy into this directory the torus example that is in the back source directory. So this is in the back directory. Then tests are MHD for relativistic MHD, and then there are different options And let's run again the configuration line. So this line contains again the web information that we said yesterday, but to recall, here this minus b gives the number of dimensions and the number of directions, so the number of dimensions of the problem and the number of vector components. Here is 2 and 3. And now, because this simulation is in spherical coordinate, we have to choose which coordinate will be the y direction and which coordinate will be the z direction for the theta direction. In this case, so yesterday we just skip over this parameter because the shock tube was in Cartesian coordinates, but now we will set phi to the direction 3 and theta to the direction 2. And because the simulation is only in 2 dimensions, we are setting phi to the direction 3, so actually we will be simulating on the meridional plane. So not on the equatorial plane, but on the meridional plane. Then, because now we are making a simulation in 2 dimensions, we will give to the minus g flag that gives the extension of each of the AMR blocks 2 numbers. So the first one will be the number of cells in the radial direction, and the second will be the number of cells in the theta direction. We are again setting the type of physics to relativistic MHD, the equation of state to Gauss and Euler-Curie, and the coordinates to, in this case, now are no longer Cartesian, but now the coordinates are also modified per shift. So it's just the same type of coordinates that we use for the GRP simulation.
So after yesterday, you told us to change Fortran to Fortran 10.
Right, exactly. We will do exactly the same now.
Right. Thank you very much.
Right. So indeed, for the architecture file nowadays, I just skip to keep it at the end, but indeed we will change it to Fortran 10. Okay, and now that the configuration file has been set up, let's just make. So all that I am doing is exactly the same as it is in the tutorial. So I will just not put it side by side because the script becomes very disordered, but it is exactly the same steps. So in the meantime, while it is running, I can explain some of the, well, it is compiling right now, but I can explain a bit more how the adaptive error finding is working. So we have this parameter that we set that was minus g, and we set it to 24,16. So this parameter will give the total extension of the blocks that will be distributed among the CPUs. But this total extension is given including the number of ghost cells. So in the simulation, let's say that this is the meridional plane, will be divided in several blocks. And these blocks will be of a given physical extension. So we can call this, let's say, n theta and n r. So the physical extension of these blocks will be precisely that number. In R and n theta. But the total extension of the block will be found by adding to n r and n theta the extension of the Gauss regions. So this is a fixed number so currently the same amount of cost regions is used in every direction, and this is called in back the ISP. So we then need to select a base resolution that will be this, that in this case it is 48 by 24. And this base region, this base resolution needs to be an integer multiple of NR and N theta. So this would be the number of cells in the radial direction. So which in this case, this is 48. And the number of cells in the theta direction, which in this case is 24. So this number is the total size of blocks, including those regions. Here we are setting, well, all of this that I'm talking about is explained here. But here we are using a value of the closed cell region of 4. So this means that that in this radial direction we have to subtract 2 times 4 from 24, so that gives 16, and then NR is equal to 16. And also from 16 we have to subtract 2 times 4, that gives 8, and then N theta is equal to 8. Therefore the resolution in the radial and theta direction needs to be respectively an integer multiple of 16 and 8. Now, given the resolution and the clock size, the other parameter that we need to give in order to control the adaptive refinement is the number of layers of a map. So this is given by this parameter that is called NX nest. In the first case, this is 1. So this means only a fixed resolution. That will be this 48 by 24 resolution. So, now this has finished compiling, we can try to see what happens if we run with these parameters. So we can open the parameter file. And set actually here the parameters are different. So here we are having 2 levels of refinement and 192 cells in the radial direction and 96 cells in the theta direction in base resolution. Actually, maybe instead of trying to change the resolution as it is in the tutorial, I will run it with these parameters just to show you how the initial condition looks. And maybe I will give so I will give you the task of following the rest of the tutorial, and you can ask me questions maybe later today or in the next day. So to do this, let's just run the code. I will send the output to this file. I should also create an output directory similar to yesterday. So I run this. And well, this has already finished. So because we only asking for run for very few iterations. And then let's have a look at the output. So it has produced some files. Let's have a look using the Python tool, which is something that is also explained here in the tutorial. Okay, so now we have read all the variables, and so just to finish, I will try to plot this. So all the commands that I'm using are from the Python tools of back. So you may not recognize them because we didn't go through this, but all of this is also explained in the tutorial. So we are looking, actually let's just copy from here. So we will be looking at the logarithm of the density. So this should produce a figure. And so as we wanted, we have a slice of a torus in the meridional plane. So this will be a simulation that is assuming the symmetry in the phi direction. And so this is the inner radius of the torus, and so what we are seeing here is the torus, and here is the black hole. Inside the user file, as I was mentioning yesterday, there are some parameters that one can change in order to set up the torus differently. So just to give a quick look. We have here these parameters. Oh, this is very much in the where one can set since as the adiabatic index of the fluid, the speed of the black hole, the inner radius of the torus, and the position of the density maximum in the torus, the gravitational gradient, as well as other things like a measure of the magnetization, and some other parameters related to how many magnetic loops one starts with in the torus. So unfortunately, I don't have more time to go through this in very much detail. But if you want, you can try this yourselves we'll try to follow the steps of the tutorial. And if you would like to know more or have any questions, you can contact me during the remaining days of the school. So tomorrow, I am planning not to have any more practical sessions, but instead to show you a bit some of the applications of physics in my own line of research, that is on trying to predict the observational appearance of exotic compact objects. So that's it for today. Thank you very much.
Thank you very much, Héctor, for your lecture. Do you have any questions?
Thank you very much, Professor. Just to become clear, where was the information about the geometry that I'm considering in the code?
I see. So in this, you're doing about the geometry, let's say, of the torus?
For example, in the previous data, I'm looking at what is the geometry that I'm considering when I have 4 features that you showed in the first case. The second is the torus. And the first case, what is the geometry that I was considering?
Okay, about let's say the metric, no?
Yes, yes.
Okay, that is a very interesting question. So the way backhand handles the background geometry is by specifying coordinate files. So previously, when we set up when we chose the MKS coordinates, so here we chose to use the modified curve coordinates, but there are several different choices that we can make. So one can find all the possible choices in inside the source directory. In a directory that is called geometry. So here you can find all the types of coordinates that is also the types of metrics that are already available in the code path. So now if one looks at the code paper, so here in the code paper there is a description of what is all of every of the different options that are in this coordinates directory. So we would have, for example, Boyer-Nyquist, Cartesian, Herschel, but a lot of some non-standard things such as, for example, the Revology angle parameterization. What is there here? Also this non-rotating needle and black hole. Or there is also the option to use numerical spaces. So actually, so even if it is not available in the website because it is not very polished, there is also a tutorial on how to add a numerical spacer to this to back. In that case, one has to prepare a file with a specific format, and instead of setting -4 equal MKS, one can And finally, one can also edit, and one can also add a new coordinate file. So one just needs to fill in the function that describes the metric. And if one wants to implement an analytic metric, that is probably the best option. Something that is nice about the coding is that in general you don't need to provide the derivatives of the metric. If you use a numerical metric, the derivatives will be calculated using finite differences. And if you use an analytic metric, the derivatives will be calculated using a technique that is called the complex step derivative, which is a very nice and a very clever numerical method that calculates the derivatives at machine precision by making a small step in the complex plane and using the Cauchy-Riemann relation. So for numerical metrics, for analytic metrics, that is something possible and very nice to do. And from the implementation point of view, the nice thing is that you don't need to provide a derivative, just the expression for the metric component. But if you are interested in this, we can also talk more about it afterwards.
So, do we have any further questions? If not, let's